Columnar representation allows us to do a bunch of different things very efficiently. So for example, it's much easier to compress data in terms of the columns of that data than the rows. So if you take Netflix data, which has 1.4 gigs raw and about 289 megs if you compress it using gzip, you can compress it using this columnar representation and do some really interesting things. So there's 3 columns here. Our compressions are sharded, so they're cut into different pieces that don't necessarily align with each other, but it speeds things up, and saved in disk in a continuous way. And we use all sorts of compression schemas that are kind of off the shelf, and you're welcome to try this out. This is all available in open source. And if you do that, allows you to take this data set, compress the user column to about 176 megabytes, the ratings columns to about 47 megabytes, and interestingly, the movie column to just 257K. And in total, you end up with an even smaller file than you did with gzip. But one that allows you to do a lot of the computations that you might want to do with machine learning extremely fast. And building this representation only takes a few seconds on my desktop. So let me show you a demo of that. So today I'll be doing a few demos, and they're all going to be on my console using Python. So unlike, I hope you're prepared to do some coding together. So this is the first demo. I'm going to read the data set, and this data set is a bio data set, so biological data. I'll talk about it in a second. But just so you know, it involves 950 columns and 931 million rows on one machine. So this is running on a single machine. And here's what the data looks like. There's this variable y that you want to predict whether life is viable or not, depending on a bunch of different mutations that have been observed in the genome for different subjects, for different experiments. And some of these mutations are binary, some are integer, and some are numeric double values. So this is a really big data set. If I didn't compress it at all, it would be about 5 to 10 terabytes of data. And again, just want to remind you, I'm going to run this on a single machine. And so you can look at a particular row of that data. And by the way, this is one of the hardest tasks because the data is stored in columns and we have to kind of pull it out as a row. It's not so easy. But you see, it happens pretty quickly. And you'll see exactly what I showed you. There's some zeros, there's some ones, there's some numeric values, and so on. Now, let me show you a few operations that you can do fast using disk if you have this representation. So I'm going to take the column y, and I'm just going to compute the sum of that column. So this is the sum over 930 million rows on a single machine, and it took 2.04 seconds. Not bad. Let me take another column. That was an integer column. Let's take a float column, which has 931 million rows, and compute its sum. Now, if you're thinking about doing feature engineering, you're going to do all sorts of transformations. This took about 2.05 seconds, so still really fast. And actually, we have a visualization tool that allows you to explore the data. So if I type .show on any data structure that we use, you can actually visualize it. And what you'll see here is, actually, the font is a little too big to see. But what you'll see is this 10 terabyte data set being open on a browser, and allows you to explore the data set in all sorts of ways. And I'll show you a more detailed demo of this in a few minutes. But increase the font again. Let me show you, remember the transformations we described in feature engineering? This is a really big data set. I want to create a new feature called myColumn, which is the sum of a few other columns. Let's see how long that takes. And then I'm going to sum that column so I can perhaps normalize it later. And so again, this is 4 columns. Each one has 930 million rows, and I'm running a single machine. It takes about 8 seconds. So it's pretty damn quick. It's pretty cool. So this is the kind of thing that you can get from columnar representations. Let me show you some more detailed benchmarks here. So show the last scale demo. So maybe not. I kicked the wires, so you guys know. Okay. No, yes, maybe. It's a definite maybe. Okay, let's try this again. Let me show you some benchmarks so you know the kind of performance you can get if you decide to use a columnar representation. So take a tabular transformation benchmark, which has been done by a bunch of different people. This is we just copied the numbers from a recently published Sigmod paper. You try this using S-frames. You get really fast results, best of the lot. And all these were running on 5 machines while we only had to use 1 machine for us. And it also allows you to do other things quickly. So for example, the deep learning demo that I showed you a little earlier, it's really fast. So as a benchmark, you can use H2O's deep learning implementation with 63 machines. This is from their website. Or you can use a single GPU and process more images per second than with 63 machines. And it works for graphs too. So for a long time, I've been obsessed about graphs, and many of you already know that. And you can imagine computing PageRank on a graph. But in real-world settings, data doesn't come to you as graphs. Often data starts as, say, raw text from Wikipedia, which gets transformed as a table, which then gets transformed as graphs. So you have to interact between tables, graphs, and text. And part of what we did in the design of S-frames is provide one representation that can deal with all sorts of different data types. And it's really fast. So we can use S-frames, which is a columnar representation for tables, and S-graph, which is a columnar representation for graphs. And they can be changed between one and the other with no loss. So in terms of performance, if you take the Common Crawl data set, which is the biggest publicly available graph out there, it has 128 billion edges, 3.5 billion vertices. There's been very few benchmarks published here, only ones done with proprietary hardware, so it's hard to compare. But so you know, we can process this on, for about 9 minutes per iteration of PageRank on a single AWS machine. And another benchmark that was done by others, if you take a graph analytics task and you try to use Spark, Giraffe, GraphX, those tend to be quite a bit slower than what you get with this representation. Those numbers were running on 16 machines while mine was running on a single machine. So the first part of the talk is to convince you to go and explore columnar representations of your data. I think ours is pretty unique and nicely done, but all sorts of other opportunities out there, but definitely something worth exploring and worth investigating. So in the second half, I want to talk more about deploying machine learning algorithms. So as I said, I typically thought about machine learning as just having 2 steps: data, machine learning algorithm, write paper. This piece is typically done by the data scientist. But in practice, if you're working at a company, you know there is a whole other piece of the equation, which involves data engineers, data architects, DevOps, app developers that take the outputs of that model and integrate with a real-time application. And this process is annoying. It's slow, time-consuming. So typically what happens is this team over here writes something in R or Python, then it hands it over to this team over here that re-implements it in Java or C. That process can take 6 to 12 months, and in the end, the thing that gets implemented had nothing to do with what you originally hoped for. Becomes stale, irrelevant, and requires 2 teams to maintain 2 different systems. So we want to make that easy. Let me talk about a few design principles that you might want to follow if you want to build such a system. So the first thing is that you want it to be easy to integrate so that the app developer team doesn't have to do much work. And this is where RESTful APIs come in. That allows you to interact with your model in a very simple way. We also want it to scale and to be robust to failures. So we want some replication of your model across different machines. We want a caching layer. You want simple APIs, a load balancer. And on top of it, you want to deploy not just models that you run using GraphLab Create, but anything you build, let's say scikit-learn models or anything in Python. So this is what typically people would want in practice. Build something like this on the right. And you can do it yourself. Here's some tips. For the web services, I recommend Tornado. You can also use Flask, Django, and other things. For the caching layer, you can use Redis, Cassandra. There's many opportunities. You also have to log your results, so you might use something like Logstash or one of these other tools. And you also have to keep your metrics going, so maybe if you're on AWS, you use CloudWatch. So these are the pieces that you have to combine and maybe have in order to deploy a machine learning algorithm model in reality. And because this process was slow and painful, we built something that we call predictive services that makes this whole piece easy. So let's say that you have a front-end application you want to build that uses machine learning, and you're the data science hero on the left, and you build this awesome model. The question is, how do you connect the two? And so what predictive services allows you to do is get a robust, scalable system that can deploy any model. It can be built with GraphLab Create, it can build scikit-learn, Python, anything you want. It gets hosted in this robust architecture so that when your users of your website, let's say users of Quora, come in, they query the website, it directly goes and queries the cache layer of the model and comes back with a recommendation of what answers they should be looking at. And if in the meantime you get new data, you come up with a better model, you want to A/B test it or you want to deploy it, you can redeploy it with no downtime. And the design follows many of the ideas that are described in the open source version in the previous slide. So let me show you a last demo for today of what this looks like. So that's also not what I wanted. This is what I wanted. All right. So this is what I'm going to do. This is Python, so I'm just going to import GraphLab Create. And I'm going to read some book review data from Amazon. So this data, the first thing you want to do is do the data engineering and exploration piece. So let me look at the first rows of the data. So there's a user who recommended an item. They had a title, had a price. The user had a profile. There was a score of the review, and so on. Now, typically, you do some transformation of this data, plot it, compute summary statistics, and that will take a bunch of time. And it was taking our team a bunch of time. So we built a data visualization companion where you can type .show on any data structure that we generate and come up with a visualization for that. So these are book reviews. So you'll see that it goes column by column and uses a one-pass sketching algorithm to come up with a summary of what's going on in that column. So for example, for book titles, the most commonly reviewed book is Harry Potter. Makes sense. The average book price is $22.56. The highest price was $104. And it goes on, profile, gives you summaries. So for example, this is the summary of the reviews. Let's see what happens when I click on it. I get a sketch, and you see these are book reviews. So the most common book review summary is great book, followed by great book, followed by excellent, good book, great, great read, excellent, amazing, and eventually disappointing. So in a few clicks, what did I learn? Most reviews are positive. So for example, if you're minimizing squared error, bad idea. So what should you do? You can build a model from this data that tries to capture whatever results are in that data. So for us, we have a bunch of models that we pre-implemented. You can also use scikit-learn models if you want. But I'm going to just call recommender.create, where we look at your data and we make an automatic decision of what model should be the baseline model for you. And since this data is mostly positive answers, we use item similarity here. And in a few seconds, we'll have a recommender model. So now, if I were writing a paper, I would be done. I just compute a ROC curve, and the story ends here. But I want to do more. I want to recommend books to people. So for example, Sean, that works with me, loves the John Adams biography by McCullough. So what other books should he read? And so 1776, the Roosevelt biography, Lincoln biography, and so on. They all make sense. But I don't want every time somebody goes to my website to have to go in and type their name here and get the query going and so on. I want this to be an automatically deployed machine learning model. So again, with predictive services, we make that easy. So what I'm going to do is connect to a predictive service that we have running on EC2, and I'm going to type .show on it, and you'll see on Canvas what that service looks like. So I'm going to decrease the font a little bit. So there's 3 machines in parallel, and it's currently all up. So now I'm going to call this model Carlos Recommender Model, and I'm going to deploy it. And depending on how fast the wireless is, what happens is this model is built on my laptop, because the demo is my laptop. It gets copied over to an S3 bucket. Those 3 machines read the model and automatically start serving it through a RESTful API. And if you come up with an updated version of the model with more data, or you want to compare to, you can deploy that, you can compare the two, you can transition with no downtime. So now it's been deployed, we can now query it. So you can use RESTful API anything you want. You can use JavaScript, you can use Python, you can use curl if you want. Here's, I'm going to do Python. So here's a particular user in Amazon. I'm going to see what books to recommend to this person. And you'll see for this person, the most important read is Practical Demon Keeping, a Comedy of Horrors. And there you go. So in that process, just wrap up here. Maybe not. Okay. So in that process, what we've done is taken the model that we built on the laptop, deployed as a service that could be queried in real time by the application. So now let me talk a little bit about what we're doing at Dato. So at Dato, we're really trying to make a platform that makes it easy to build, deploy these machine learning tools. At the very core of it is the S-frame and the S-graph that I described in the beginning, which are data structures for large-scale analysis. And those are available in open source, so you can go use them whatever way you want. But we also offer GraphLab Create, which has more advanced machine learning tools and data visualization opportunities. And we have developed deployment tools both at scale, where you deploy distributed machine learning algorithms. This is the data distributed part, as well as the services, predictive services, where you can host your machine learning models and query them in real time in a robust way. So just to close off, I'm really excited about the place we're in industry. I've been working machine learning for a long time, and this is the time where building machine learning applications from that initial inspiration all the way to taking them to production has become a reality. And this is really fun for me. And so my goal is to make that easier and make it possible for more people to go through these tasks more quickly. Thank you. I'm not sure if we do questions or no questions.